Hi, my name is Dr. Gareth Edwards, and I'm here to talk to you today about Robotti, our autonomous agricultural implement handler. As a co-founder of Agrointelli, an agricultural innovation company out of Denmark, Northern Europe, we've been developing Robotti for the last 7 years. I'm going to start off by giving you a brief history of Robotti and the company Agrointelli. How we started from a small research project to become a fully fledged product available and currently running in four continents across the world. I'm then going to go on to talk a little bit about our cloud architecture and some of the design decisions I made when we were constructing it. I'm then going to move on to talk about some focus areas where I feel that we're doing some good work. Firstly, we'll be talking about simulations, how we use that part of our development and deployment. I'm going to talk about fleet coordination, how we coordinate small operations in the cloud. And then I'm going to talk about image collection and utilization, how we're collecting images to be able to progress with Agricultural 4.0. But before I can talk about Agricultural 4.0, I need to talk about Agricultural 1.0. And that was the domestication of robots. Domestication of agriculture. So, here's an image from Agricultural 1.0. To start off with, we had a horse and a human working together in synergy. This was a good tech setup and had a lot of advantages. The whole system ran on biofuel. We had wireless communication between the farmer and the workhorse. Often it could respond to verbal commands. The farmer had load indicators from the animal giving him feedback all the time, and he was able to inspect the outcome of the work close up using his 3D cameras. Since then, we've progressed into Agricultural 2.0, which was mechanization, and Agricultural 3.0, which was industrialization. With these two leaps, we've increased the capacity of what one person can do, making him carry out more work in a shorter amount of time. However, we've also removed the human from close inspection of the ground, and we've also started using bigger machines which increase the pressure on the soil. At Agrointelli, we want to move agricultural forward, but also backwards. We want to give the farmer an in-depth understanding of what's going on, but also we want to save the soil. So, Robotti first had its seed planted in a university project in 2003. From there, it grew with the idea that it was easier to do repeatable experiments if it was a robot driving the tractor instead of a person. In 2012, it was bought. The project was bought by Kongsberg, which is a Scandinavian implement manufacturer. However, in 2015, due to some internal restructuring that they were doing, the project and R&D researchers left the company, and we started Agrointelli. Since 2015, we've been on a mission to commercialize and develop Robotti, so it's available to ordinary farmers. And now we're at a point where we've got several seasons of work behind us, and we can scale up, making it available not just to the early adopters, but also to the first movers. So, our Robotti, what is it? Our Robotti is our agriculture, as I said before, is our agricultural implement handler. It's a robot with two 150 Kubota engines built by the Japanese manufacturer Kubota. It has a full hydraulic drive chain, which gives us a good power conversion as well as being easy to control. It has a total weight of just over 3,000 kg, which is about 3.4 tons. This is about half the weight of an average tractor. So we're putting a lot less ground pressure on the soil, which helps maintain its structures. We have a standard 3-point hitch, a standard hydraulic setup, and a standard PTO, all of which means that we can attach standard implements to it. So there's already a wide range of implements already out there that we can use. We have an RTK GPS with an infused IMU, which gives us sub-inch precision, which is very important when we're doing agriculture. And we have 3 onboard computers. We have a VX Box 3150, which runs Ubuntu and ROS and handles all our high-level control and our communication. And we have an X90, which handles low-level control and safety, And then we have a NVIDIA Xavier, which handles all our cameras and image processing. So our current fleet. We currently have 30 plus robots at places all across Europe. There's about a 50-50 split between robots that are with research institutions and universities and that are with commercial farmers. We also have robots in Azerbaijan, Australia, and one heading over to North America. I couldn't include them on the image here because that would mess up my scaling. Our current business model has been to employ dealers in every region so that they can handle the first contact with the farmers and handle first line support. This relieves some of the support tasks from us developers. However, because the robot is autonomous, it can run 24 hours a day, 7 days a week. Therefore, we need a very robust infrastructure to be able to support that so that we don't get calls in the middle of the night. Our web application is where farmers can interact with their robot. They can view live operations. They can know where it is and what it's doing. If it's doing an operation, they can see how much it's done and how long is left. They can also stream video from the 2 onboard cameras, and they can stop an operation if needed, although they can only restart it again if they're local at the robot. They also use the web application to create plans for future operations. Now, farmers are very particular about their fields. It's not a case of just putting the robot in the field and pressing go and letting it do whatever it wants to. Farmers know how they want to work their fields and why they want to work it that way. So our planning tool allows them to go in, upload files, and select about 80 different parameters to customize plans to what they want. The farmers are also able to visualize what has already been done and look into previous operations. This is actually very important in Europe because a lot of the operations have to be registered with the government in order to deal with regulations and subsidies. On our web application as well, we also have a number of engineering tools so that our developers can monitor the robots and also deploy softwares to one or groups of robots too. Another user interface we have is our terminal, actually on the robot. This is where users can select and start plans, they can change robot settings, and they can record fields. And finally, we have a physical remote for manual driving. This has 2 thumbstick controllers, which is extremely intuitive and actually quite fun to drive. It also has an emergency stop there for emergencies. So I'm now going to go on to talk about our cloud. As we were developing Robotti, we made our own cloud infrastructure to be able to support it. This worked for a small number of robots, but as we started to increase our fleet, we found it was needing more maintenance, and it was hard to put structure in where structure hadn't been built in from the beginning. Therefore, in 2020, just as the pandemic was hitting, we decided to take this opportunity to move across to AWS. The goal was to create a reliable and scalable infrastructure that could handle our operations and minimize the maintenance burden on our developers. We also surmised that it would be easier to onboard developers in the future if we were using a structured way of doing it rather than our own home-baked solution. So the move went well. And in just under 6 months, we managed to move completely away from our old system and turn off our cumbersome servers. So I mentioned earlier that our farmers are very particular about how they create plans. I'm now going to go on to talk about the infrastructure that we use to be able to build these plans. So here you can see our cloud infrastructure. We have the website. That's where the farmer logs in and can upload files describing their field shape, their obstacles, and change parameters such as what implement they're using, how fast they want to drive, what direction they want to drive. Well, as I said, a lot of parameters that they can choose there. Then our web application running on Elastic Beanstalk builds all these parameters together into a JSON file, which we store into an S3 bucket. There is a trigger on the S3 bucket for when we insert the JSON file that fires up a Lambda. This Lambda function saves data into our RDS database and then looks towards our auto-scaling group to find a place on one of our servers to run the planning. We did experiment to start off with to see if we could do our planning on a Lambda function. because we thought it'd be quite good with how scalable they are. However, these plans are quite complicated. At their heart, they're a traveling salesman problem. However, in the field, there's no roads, so first we have to build the roads before the salesman can drive anywhere. Therefore, we developed a solution where we're creating Java servlets, which run on EC2 instances. These run within an auto-scaling group so that they can be scaled up and down dependent on demand. So our Lambda function sends the JSON to our auto-scaling group, which does the first planning and creates a plan, and then puts an output JSON back into the S3 bucket. I'm now going to go on to talk about how we start an operation. So from the robot, as I said, we have the terminal. On this terminal, we go in and we can select a plan. To give you a bit of background about our data structure, we have a plan, which is kind of the instructions of what the robot wants to do. Each time the plan is run, it creates an operation. This is the work for the robot to do the whole plan. If a plan is run several times during the season, that's several operations. Under each operation, we then have a number of tasks, which is a smaller division of an operation, which can be done by one or more robots. So when an operation is paused, the task is ended. And if it wants to be resumed, we can resume from the end of the last task. So when a user goes into the terminal, they can select a plan, and they can see if there's an operation there to resume or not. They fire a message using our IoT, which kicks off a Lambda function. This Lambda function retrieves the input and the output from the S3 bucket and collects some operational data from our IDS database and from our Dynamo database. I'll go on to talk about those on the next slide. Once the Lambda function has this data together, it then looks to put it into the auto-scaling group again to run more planning. As I said, the planning takes a long time, but when the robot is placed in the field and a plan is chosen, we don't always know exactly where it's going to be placed. So when they start the plan, they're updating the start position, and there's also some parameters about the robot that they're updating. So we need to run the planning again. However, this time it's much faster, approximately 10 to 15 seconds. Once the planning is finished, it outputs a set of instructions for the robot, which are stored in a RDS database. In a Dynamo database. When the robot then wants to start the operation, it has another endpoint where it can send a message through the IoT and retrieve these instruction sets. The final architecture I want to go through is about how we monitor the live operations. Again, this is another task that the web application runs. So we have our robot at the bottom there, and that sends its position, its operation status, and telemetry through using MQTT through IoT. This triggers a Lambda function. This Lambda function works out where it's going to store the data. When we first moved to AWS, we had all our data stored in an RDS database. However, as our fleet began to grow, we noticed that through the live monitoring and other operations, we were causing a lot of connections to be built to this RDS database. And even though we had it in an auto scale, we could actually, the amount of requests being made to it could actually block it. As you saw on the previous slide, we need access to the RDS database to be able to start operations. Therefore, it wasn't acceptable that we couldn't have access to that and we couldn't start operations. So we had the idea of moving our telemetry and our location data into a Dynamo DB. This data is only needed on a short-term basis, and it's putting it in the Dynamo DB makes it easier to retrieve. So that's what we did. The Lambda function stores the data where it needs to be stored. There's also triggers on when the operational status of the robot changes, where it can compile all the short-term data for a robot into a JSON and store it in our archive storage for retrieval later. So when the user wants to view the live operations, they log onto our web application, again running on Elastic Beanstalk, and through an API gateway and a Lambda function, they're able to retrieve the data about the current operation and what the robot's doing. We also have another connection there from the robot to the website where we are able to stream live video. When we first started again, we were using signaling channels, as it was a requirement that we were able to see the video from the robot with the least amount of lag. However, using the signaling channels meant that we had a peer-to-peer connection between the website and the robot. This wasn't ideal, because if many people were watching the video, as is the case if we had a farmer, a worker, and a service person, then that was 3 connections being made to the robot, eating into its bandwidth and making everything not work. Therefore, we shifted over to using video streams. This introduced a larger lag, but again, not too bad, about 10 seconds or so, which was still very workable. But the main key being that it didn't eat up all our bandwidth. I'm now going to go on to talk about some of the focus areas where, again, I think we're doing some good work. So I'm going to start off talking about simulations in our development and deployment. With Robotti, we use simulations as part of our functional integration testing, as well as our development testing before deployment. This is really useful for us because when we're developing in the cloud, we can quickly test with a simulation if the integration is working, and also then before we deploy software, we can again check that all the code is good, so we're not deploying bad code to our robots. We also use simulations for model training. We have a number of behavioral algorithms on the robot for things like path following and for collision avoidance. These algorithms all have a number of parameters. So using the simulations, we can parameterize the models, and we can do parameter sweeps, and we can calibrate them so that we can get them performing as best we want them to. We also, with the simulations, we have 365 days of testing. Since we're working in an agricultural environment, there's actually only a small window when we can actually get in the field and be able to test under real conditions. Those are also the times when the farmers are in the field themselves and need everything to go right. So, using simulations, we can test whenever we want to, and we can also test in different environments. We can parameterize the simulations so that we can test on different soil types, not just the soil types that we find in Northern Europe. We're also expanding the simulations, working with some universities at the moment, looking into digital twinning. At the moment, this is mostly done for part fatigue control for our service department. However, we're also looking to expand it into logistical planning. So we say all the world's a test track. Like everyone else, when we started developing in ROS, we were using Gazebo to do our simulations due to its easy interfaces between ROS. However, Gazebo doesn't allow us to put a deformable surface underneath our robot, which is fine when you're developing robots that work in warehouses and work on roads. However, how the robot interacts with the soil and how the soil interacts with the robot is of great importance to us. Therefore, we decided to develop our own simulation engine. Using the Chrono physics engine, we developed equations and models to be able to create terrains for all kinds of soil types. We built our own ROS interfaces so we can easily interface with it. And then using the recent updates with AWS RoboMaker, we're able to run this in the cloud as part of our deployment. This makes the whole integration really easy and really easy for our developers to use it. So this is an overview of our deployment architecture. As you can see, on the left here, we have a number of code repositories. We have a code repository for each one of our computers on the robot. When our developers push new code to these repositories, a build pipeline creates the files and puts them all in an S3 bucket. It's from here that we can directly connect to RoboMaker so that we can validate that the code that we've just pushed is still working as we want it to. Once the code has been validated, there's a second pipeline that's initiated by the developer, which puts the binaries in 2 repositories and in an S3 bucket. So then when a developer wants to deploy the software, they go onto our website and they can update the device, a parameter on the device shadow. We have green grass installed on one of the computers on the robot, which monitors the device shadow. And when it registers as delta, it prompts the onboard computers to download new updates, and install them. When we were kind of developing this, we looked into using green graphs for the whole development, not just the whole deployment. Sorry, not just for the working as an agent. However, there was a number of limitations with green graphs due to the persistence of the updates that we couldn't work around. Therefore, we developed our own solution. I'm now going to go on to talk about how we do planning for the collaborative operations using a state machine in the cloud. So, in our sector, there are a number of different operations, operation types. First, we have serial operations. This is when one machine drives first and another machine drives after it, normally following the same route, but every part of the field gets worked by the first machine and then the second. An example of this might be tillage or seeding. The second type of operation would be parallel operations. This is when we have two machines in the field, each working their part of the plan. So as such, each part of the field is only visited by one of the robots. In both of these two types of operations, collision avoidance is important, and we want to keep the robots as far away from each other as possible. However, in the third type, cooperative operations, the robots are actually helping each other. For instance, in a seeding operation, one robot could be seeding, while the other is driving backwards and forwards to a silo to collect seed. In these type of operations, the robots don't avoid each other, but actively seek each other out. So we have to make sure they're driving where we want them to, when we want them to. That's why we do the planning in the cloud. When we were constructing the state machine, we had two options. We could either have a state machine for the planning in the cloud, or we could have state machines on each individual robots with planning modules there. So we kind of looked at the pros and cons to see which would be the best solution. So if we use a cloud state machine, we have a God's eye view of the system. We have all the available data about all the available robots that's possible to have at that time. And we have one point of truth. That is what the cloud knows. If we were doing edge computing and having the planning on the robots, then we could have each robot can have a different idea of what its own self is and what everyone else in the fleet is. Therefore, each one has their own point of truth. Then, when they're doing their planning, they could come up with their own optimized plans. And we'd have to negotiate between the robots to work out which plan was best. However, doing it in the cloud, we've got one point where we were doing the planning, and the plan that the cloud creates is the plan for the fleet. One of the cons of this is that we have to have good connectivity. We need to be able to communicate all the time between the robots in the cloud so they can send us their position and we can send them their instructions. While this is a downside for us, especially because we're working in rural environments, it's a problem that can be solved with more technology, such as increasing Wi-Fi points in the field. We also found that we need a good connection to be able to run some of our other systems. So even with a bad connection, the robot's not going to work anyway, so it doesn't matter. Another con is that it's a large computing effort to do this planning in the cloud. It has to create a plan for the whole fleet. However, since we're using AWS, the planning effort can just be spun up, more servers, and we can mitigate it that way. And in fact, if we were doing it on the robots, we'd be sucking away some of their resources, which they wouldn't be able to then use for path following and for collision avoidance. So here you see the flow of the Lambda function that we use for the cloud state machine. As I mentioned before, we have a plan, we have an operation, we have a task, and then we have an instruction set. These instruction sets are sets of instructions which could include things such as follow this path, engage implement, follow another path, disengage implement. Each one of these instructions also has an associated goal state, which could be its position, its orientation, velocity, load, time, any number of parameters. So when the instruction set is made, we also have these goal states. So the cloud state machine is triggered each time the robot updates its position and updates its current state. We take that current state and we retrieve its current instruction set. Using the current instruction set, we then predict what the goal state will be from the current state. Using this predicted state, we then compare it to the goal state. Now, it's very important that the robots are on plan, especially when we're doing planning with multiple robots, because if they start getting off plan, then they can start running into each other. So we compare the predictive goal state with the actual goal state. And if they're within tolerance, then everything's okay. But if they're out of tolerance from each other, such as the robot is running late or early, we need to initiate a replanning for the whole fleet, taking in the current states that we know in the cloud and then creating new instruction sets and sending them out to all the robots. As I said, if the robots are within tolerance, we then go on to check what the current goal is, the current state is against the goal state. So we can see if the robot is nearing the end of its instruction set. If they're far from each other, that means the robot still has a long time on its instruction state and everything's okay. If they're close to one another, that means that the robot will soon be coming to the end of its instruction set and we should send it its next instruction. In this way, we only give the robots their instructions as they need them. This is so if we have to do a replanning, it's easier to replan instructions that we haven't yet sent to the robot rather than cancelling instructions that are already on the robot. I'm now going to go on to talk about how we use image capture to support Agricultural 4.0. As I said back at the beginning of the presentation, Agricultural 4.0 is digitization of farming, being able to use the advanced systems to be able to make agricultural operations better suited to the ground conditions that they encounter. So this is the architecture of how we bring images into the cloud. First of all, we have two routes with which the images can get into the cloud. We have the robot, which is continually recording images from downward-facing cameras. The robot then uploads a ROS bag with these images, uploading about 1 in 30. It could upload more, but again, in order to limit the amount of bandwidth being used, we only upload one every 30. The other ROS bags are saved on an SD hard drive, which is plugged into the robot. When the operation is finished, this hard drive is then taken back to the office and plugged into an upload terminal, which we've created ourselves, which upload the images to the cloud in exactly the same way that the robot would have done. So all these ROS bags arrive in our image ingestion S3 bucket. When on insertion, a Lambda is triggered, and if it's a ROS bag, we put it into a queue, which then sends it on to an ECS instance, which pulls the image out of the ROS bag and puts the PNG image back into the S3 bucket. This time, another queue is triggered on the PNG insertion, which feeds the PNGs to a Lambda function, which does some pre-image processing. It does some color balancing and some contrast manipulation to make the images more machine readable. These processed JPEGs are then stored in another S3 bucket along with some metadata. Here's an image of the robot setup. As you can see, we have 4 downward-facing cameras spread across the robot. Using the user interface on the robot, users are able to select the cameras independently and select how often they take pictures. This is basically a cost balancing operation for the farmer, and it depends on what they want to use the images for. So here is a test case at our test facility just outside Aarhus in Denmark. So as you can see, there's a large number, approximately 200 rows here in this field. And we were running an experiment to see how different crop varieties reacted to different weed control treatments. So we have 5 crop varieties that we want to sow in this field. They're randomly assigned to different rows, and then the robot goes out and sows each crop variety. This task is actually really well suited to the robot because it can all be planned ahead of time, and the robot can effortlessly carry it out with a lot of precision. Once the crops have been sown and left to emerge, the robot runs again, taking images as it drives. So here you can see on the left one of the images taken from the robot. It was a good place in the field. There's not much weeds, there's good emergence, and the crops are in good lines. On the right is the result of our image analysis. So the images that were in the process images that we produced in the previous architecture, we then use an outside company which use algorithms that we've developed, but who have access to agronomists who can validate what we're doing, and that can be used to classify the images. As you can see here, green is classified using green squares, yellow squares, and blue squares. The green squares highlight the plants, which is a part of the image that we want. The yellow squares highlight the thistles, which are the part of the field we don't want and which we can control with weed control. And the blue squares highlight weeds that are actually too small to control. So using that image data, we can compile it together. Each image has a geolocation from the robot's GPS, which very precisely tells us what part of the field has the weed and what part doesn't. That can be exported into an application map, which we can then import into our web planner. Using the web planner, we can create a plan for the robot, where it only drives the road where the weeds are present and only works and places a treatment over the affected areas. The traditional way of doing this would be that the farmer would drive the whole field, spraying for weeds across the whole field in order to ensure a good job is done. However, using Robotti in our plan, the farmer can save a lot of time and a lot of money on sprays, which is both good for the farmer and great for the environment. The final functionality of the image acquisition is that we can, there's a product we call virtual fieldwalk. Now we've already shown how everything can be done automatically and create the plan and weed the areas that we needed to. However, to give the farmer peace of mind, we have an interface on the web application where they can go in and choose different parts of the field and see the images collected there. If they've driven the field multiple times, these images can be viewed over time, so they can see how the development of certain areas is progressing. In this way, we're able to go back to Agricultural 1.0, where farmers could have a good interaction with their soil and their plants and get a good knowledge of what's going on, giving him the peace of mind to run the operations, also knowing the robot will do the tasks as it's created and free him up to do other jobs that are more complicated. Thank you very much for your time. I hope you've enjoyed this. If you want to contact me, you can contact me on my email at gtcedwards@agrointelli.com, or you can find Agrointelli or Robotti on Facebook and on LinkedIn. Thank you very much.